Hello, class. Today we're going to go over some notes related to alkane nomenclature and how to name alkanes using IUPAC rules. So first thing we need to know is what an alkane is. An alkane falls under a larger group of compounds called hydrocarbons. Hydrocarbons are organic compounds that are composed of hydrogen and carbon only. Some examples here are saturated hydrocarbons or unsaturated hydrocarbons. If it is saturated, that means that every carbon has 4 bonds, and when it is not bonded to another carbon, the rest of those bonds are hydrogens. When we have an unsaturated hydrocarbon, that refers to a double or triple bond that occurs within the molecule, usually between a carbon and a carbon. The system that we're going to use to help name organic compounds is referred to as the IUPAC Nomenclature System. That stands for the International Union of Pure and Applied Chemistry. It is a systematic naming of compounds, so as long as you follow the system and the rules in place, there's kind of a flow chart or a way we can break down each part of the name as we put it together. So alkanes specifically are the most basic hydrocarbon. It is only carbon and hydrogen and is all single bonds. The formula for a hydrocarbon is 2 times N, where N is the number of carbons, plus 2, and that tells you how many hydrogens we have in our formula. So for instance, if I have 1 carbon, 2 times 1 is 2, plus 2 gives me 4 hydrogens. Since I've got 1 carbon and 4 hydrogens, the formula for a 1-carbon alkane is CH4. If I were to repeat the process for something larger, like something with, 5 carbons, 2 times 5 is 10, plus 2 is 12. So the formula for a 5-carbon alkane is C5H12. We're going to learn about the specific names that go into each of those alkanes momentarily, but that is the general way we get the molecular formula for an alkane. There are 2 types of alkanes. We have a straight chain, where when we look at the bond line notation, it forms this zigzag pattern. And we also have a branched alkane, where we've got a center or a parent that has the backbone of our molecule, and we've got branches or substituents, things that are sticking off of our main chain. So we're going to talk about how to name each of these. For straight chain alkane molecules, you need to refer to the number of carbons in the molecule. There's a prefix associated with each carbon and how many there are. So if there's 1 carbon, we use the prefix meth. If it's 2 carbons, eth, 3 carbons, prop, and 4 carbons, bute. And then because it is an alkane, we end with an ane ending. Now I pointed out those specific 4, this is 1, 2, 3, and 4 carbons, because those are the prefixes, the parts that come at the beginning of the word, that are different from the bottom half of our list. The bottom half, the prefixes follow the same as you would with geometry. A pentagon has 5 sides, pentane has 5 carbons. A hexagon has 6 sides, hexane has 6 carbons. So you can use that kind of format when you have 5 or more carbons. But for the first 4, they have specific prefixes: methane, ethane, propane, and butane. When we're talking about branch nomenclature, our first step is to identify the parent chain. This is the longest consecutive chain of carbons in our molecule. This parent chain is going to be at the end of our name. So in this example here, it's a little challenging. You have to find the longest consecutive chain. So if you go here, that chain, 1, 2, 1, 2, 3, 4, 5, 6 carbons long is not the longest possible chain because I could go down this way and keep going and follow like a pair of train tracks until I run out of carbons. So the longest possible chain, it seems, 1, 2, 3, 4, 5, 6. If I go this direction, 7, 8 is an option, but I could keep going. 7, 8, 9. So 9 seems to be the longest option here. And sure enough, the longest chain on this molecule is 9 carbons. 9 carbons would be nonane. So nonane will be at the end of my alkane name when I go to name this molecule. The next step is to name our branches, but a little bit more on parent chain before we move on to branches. If there's more than one possible parent chain, aka the parent chain that you identify has the same length in multiple different directions. So here we've got 1, 2, 3, 4, 5, 6, 7 carbons. And over here, 1, 2, 3, 4, 5, 6, 7 carbons. We have this issue. We have 2 possible 7 carbon chains. That is the longest parent chain. So the one we want is the one that's going to have the most substituents or the most branches. Since the one on the left has 3 branches sticking off of the chain, that is going to be the correct parent chain that we end up using. This one over here only has 2 branches sticking off of the chain and is not going to be as easy to name. So we want to use the one with more branches. Speaking of branches, those are the things hanging off of your parent chain. They can be called substituents. You can also call them side chains or alkyl groups. Textbooks refer to them in different ways, and they use all of those terms interchangeably. So the first thing we need to do is number our parent chain so that the substituents, our branches, get the lowest numbers possible. So there's 2 ways to number this first one, 2-methylpentane. The other way we could have numbered it is from right to left. So 1, 2, 3, 4, 5. Now, for the numbers in blue, I see that my first branch happens on 4. But if I number from left to right, my first branch happens on 2. Numbering from left to right is better for this particular molecule because the branch has a lower number. After we number, each substituent gets named for the number of carbons it has, and we change the ending to -il or YL. So there is 1 carbon right here on this chain. So 1 carbon has the prefix meth. Before we named it methane, so we turn it to methyl. If we have more than one substituent, they're going to be listed in alphabetical order with their number on the parent chain in front of it. We can also use prefixes if we have 2 or more of the same substituent. So for instance, if I had an extra methyl group hanging off of this 4th carbon, I could combine it and write 2,4-dimethyl. The reason we do this is for efficiency's sake. Otherwise, you would have to write out 2-methyl, 4-methyl. Not only is that redundant, but it makes the name twice as long and is a lot harder to write. Here are some examples where numbering the chain becomes really, really important. We want the lowest possible numbers for our substituents. So as I showed you before, if I number this first one up top from left to right, our first branch ends up on the 2 position. If I number it from right to left, the first branch ends up on the 6th position. The 6th position would be incorrect. When I have more than one branch, I have to pay attention to my number system as well. If I've got more than one branch, I want to list out all of the numbers for the branches and compare them. The first point of difference is where we will go with our numbering. What I mean by that is when you're looking at the first branch, if they are different numbers, you go with the one that has the lowest number. If, for some reason, they are the same number, and you have a tie for the first number. So in this particular molecule, we have a tie for our second branch. Then you go on to the next lowest number. Here, the next branch happens on 3, compared to here, the next branch happens on 5. Since 3 is lower than 5, this is the better numbering system compared to this. Now, if there's no tiebreaker, regardless of how you number it, then you're going to go with alphabetical order. So in this particular example, we have chloro for chlorine and bromo for bromine. The one where bromo is a number 1 is better than chloro being a number 1 because B comes before C in the alphabet. There are some common and trivial names that you'll need to know, things that have been called a certain name for several years and are commonly referred to as those names, usually get combined into the IUPAC system. Some of these names have just been referred to this way for a long time, and rather than trying to name them with IUPAC rules, a lot of chemists just use the names interchangeably. So some examples for that require you to know some prefixes. We have iso, which we're going to talk about stands for isomer. We have secondary, or sec, and that refers to how many things are attached to a particular carbon. We have tert for tertiary, and then we have neo, which I believe just refers to new. When we're talking about alphabetization, secondary and tertiary prefixes do not count when ordering things alphabetically, but iso and neo prefixes do count. So as I said, iso is short for isomer, and some of the isomers that we'll see are isobutane. It still has the same formula as butane, C4H10, but the attachments are different. If we were to look at the systematic name, this has a 3-carbon parent chain, which is propane, and on the second position is a methyl group. So the systematic name is 2-methyl-propane, which is an acceptable term, but commonly it's referred to as isobutane. Same deal with isopentane. It's got a 4-carbon parent chain, and on the second carbon is a methyl group. Systematically, it's called 2-methylbutane, but commonly it's referred to as isopentane. Now, these prefixes referring to primary, secondary, and tertiary carbons tell you how many things are attached to a particular carbon. So if I have a primary carbon, I'm typically at the end of a chain, and I'm attached to one other carbon, and the rest are hydrogens. If I'm a secondary carbon, I'm attached to 2 other carbons, and the rest hydrogen. If I'm a tertiary carbon, I'm attached to 3 other carbons. There's also a quaternary carbon, which you won't see very often, but that refers to having 4 other carbons attached to my carbon, and I have no hydrogens at that point in time. So the reason we need to know this is because of secondary and tertiary butyl groups. I'll have some practice for these later, but at the point of attachment, this carbon is attached to 1, 2 other carbons at the point where it attaches to the chain. Now, R refers to the rest of the parent chain, wherever that is. But at the point of attachment to the parent chain, since I'm attached to 2 carbons, it is referred to as secondary. For a tertiary butyl group, at the point of attachment, I'm attached to 1, 2, 3 carbons at the point of attachment to my chain, so it's referred to as tertiary butyl. Tertiary butyl is interesting because it kind of looks like a chicken foot or a T. Other ways you might see the tertiary butyl group would look like this. They might draw it as a T or T-butyl, or you'll see it as this little chicken foot looking shape. That'd be tert butyl. Secondary butyl looks like a normal straight chain butane, but it's attached either here or here on the chain. And then the last group is isobutyl. Isobutyl, the way I remember it, is at the point of attachment, it's attached to one other carbon directly. So it is an isomer of a regular butyl group. It also looks like isobutane. This one's not really as common, the neo prefix, but you could see neopentane pop up. That is the simplest quaternary carbon molecule, and also can be used as a substituent, and it's referred to as the neopentyl group. The last couple of rules we're going to go over are for cycloalkanes. Cycloalkanes are referring to rings. These are carbon-hydrogen compounds that form a ring or a cyclic compound. So we put cyclo in front of the name. So some of the common ones we see are cyclopropane. So this is a 3-carbon ring. A cyclobutane is 4 carbons. Cyclopentane, 5 carbons. Cyclohexane is 6, etc., etc. If it is present in the molecule, you're usually going to treat the cycloalkane as the parent, and anything sticking off of the cycloalkane will be a substituent. The one exception to that rule is when your substituent is longer than the number of carbons in the actual cycloalkane. So here I've got a 6-carbon ring, and it is attached to a 3-carbon substituent or 3-carbon branch. So since 6 is greater than 3, this is still going to be the parent for cyclohexane. When I look here, cyclopropane is 3 carbons, and it's attached to 1, 2, 3, 4 carbons. So butane, 4 is greater than 3, so butane ends up being the parent in this case. Just like we did with our methyl, ethyl, and propyl groups, we'll change our prefix, or our suffix, sorry, from ane to il. So cyclopropane becomes cyclopropyl. When we number the rings, we start the substituent out at a 1, and then we number around the ring towards the closest group. If there are 2 substituents on the same carbon, decide which one gets 1 based off of alphabetical order. So I have another example of this. So let's say I've got this 6-carbon ring, and I've got a methyl group and an ethyl group. So I would start with a 1 based off of alphabetical order on ethyl, because ethyl comes before methyl. And I have 2 ways I can number. I can number counterclockwise, or in a different color, I can number clockwise. Now, if I'm comparing my groups, I have an ethyl group on 1 and a methyl group on 5 versus an ethyl group on 1 and a methyl group on 3. Numbering counterclockwise is better because I get the lower numbers. Another example that we will see is if I have 2 things sticking off of the same branch, they both would be on carbon number 1, but then I would alphabetize ethyl over methyl. So it'd be 1 ethyl to 1 methyl. In our next lesson, I'll go over some more examples with naming, and we can apply all of these rules in practice.